Good morning, and welcome to the second of three videos on Chapter 2 in your textbook. Um, in this video, we're going to start by talking about data and some of the characteristics of data that are important before we start to actually calculate statistics. And we'll conclude this video with an actual definition of what a statistic is, and compare that to what we call a parameter. Now, so we'll start out with the definition of what we call a variable. All right, and a variable is anything that, when measured, can produce two or more different values. Okay, common variables that you would see in a social science setting, for example, are characteristics like your age, your gender, your race, your intelligence quotient, that sort of thing. It might be the reaction to a certain situation, like anxiety or anger or aggressiveness, although those are probably more on a sliding scale and result from polling data and that sort of thing. All right, no one can actually measure your anxiety, but we can estimate it fairly well. Performance on certain behaviors, your ability to recall certain facts or certain things, a quiz or a test is an example of that sort of thing. The variable that you would measure would be obviously the score on the test. And finally, situational characteristics, the environment around you, the amount of noise, the amount of heat, in other words, the temperature of the room or that sort of thing. For example, you might put two different groups of people in two different rooms, and one has the thermostat is set at 60 degrees, and the other room the thermostat is set at 80 degrees, and you compare the results of a test that they take and that sort of thing. So those are variables. Now, variables are broken up into two major categories. All right. The first, on the top of this page anyway, is a quantitative variable. And this is one that indicates the amount of a variable that's present. It's numerical. All right. You're counting how many points somebody scores. You're counting the number of, whatever it happens to be. All right. And so the word quantitative really refers to the numbers associated with a measurement. Okay. Now, on the other hand, a qualitative variable classifies an individual on the basis of a certain characteristic, some characteristic. And so, for example, it might be choice of a political party, or it might be the religion of the individual. All right, those are qualitative types of variables. If somebody is Catholic versus Presbyterian versus Hindu or Muslim or Jewish or whatever religion they are, those are qualitative variables. If you were to try to measure the height of everybody in the incoming HEOP freshman class, those would be quantitative variables, because obviously each person is 5 foot 6 inches, 5 foot 8 inches, 6 foot 2 inches, and those sort of things. There are numbers associated with the quantitative variables, whereas with qualitative, it's much fuzzier. Okay. Now, when it comes to statistics, it is far easier to deal with quantitative variables than with qualitative, because you can put the numbers into a statistical test. Now, when you compare these variables, you may determine that there is a relationship associated with the variables. And a relationship is defined as a pattern such that the scores on one variable change, or as the scores on one variable change, the corresponding scores on the other variable change in a consistent manner. And this is oftentimes represented as a graph. As the independent variable increases, the dependent variable increases as well, or maybe it decreases. All right, but there's a pattern there. There's a predictable pattern. All right, and oftentimes you would draw this. Whoops, I didn't do my pen. uh, oftentimes you would draw this as a graph. And so if this is the x variable and this is the y, as x increases, y increases. And so you end up with a relationship, okay? Of course, it could be, a different kind. It could be a curve. It could be have a negative slope, all right? It doesn't really matter what the relationship is, but it's a predictable pattern. You can see the change in one variable as the other variable changes on a regular basis, on a consistent basis. Okay. Now, the point of statistics is to measure how strong the relationship actually is, all right? So the strength of a relationship is the extent to that one or close to one value of y tends to be consistently associated with only one value of x, all right? The stronger the relationship is, the more consistent that pattern becomes. A stronger relationship occurs when one group of similar y values is associated with one x score, and a different group of similar y values is associated with the next x score, all right? And so, in other words, the more predictable the outcome of a relationship is, the stronger that relationship is said to be, okay? And so when you're looking at a data set, especially if you put it on a graph, you can, just even by looking at it, you can pretty much determine how strong a relationship actually is. Now, so when a relationship is strong, generally that means that you can go back and say, well, if x equals a certain y and x2 equals the next y, all right, then you can say, well, I would predict that x3 would equal this value of y, all right, because if it's a strong relationship. On the other hand, if the relationship is not very strong, then what that means is that you can't really predict what the y value is going to be for a certain value of x. All right, so you have to keep all of those things in mind as you go through and look at the strength of these relationships. Now, one of the easiest ways to determine, just visually now, not with a statistic yet, but one of the easiest ways to determine how strong a relationship is by looking at a graph of the data. And graphs, generally speaking, describe a relationship using the format as such. Scores on the y variable change as a function of changes in the x variable. Okay, so as the x variable increases, the y variable blank. All right. Now, I mean, you can have all sorts of relationships here. All right. If this is the y variable and this is the x variable, you might have a scenario where as x increases, y increases as well. You may have the scenario where as x increases, y decreases. You may also have a scenario where they remain, the y value remains constant as the x value is increasing. So, just because there is a relationship doesn't mean that it's always positive. All right, so just keep that in mind. All right, sometimes it's a negative slope. Sometimes it's a constant slope. Sometimes there's no relationship at all. All right, and so when you're examining these graphs, make sure that you understand what's happening to y as x increases. All right, and this is one of the reasons why we call x the given variable. All right, we also call it the independent variable. All right, because it is something that you're not manipulating. All right, you're just making a measurement of y. As the x value changes. Okay. Now, this is a graph that shows a perfectly consistent association. All right. And I like this graph because as you can see, there's essentially a perfectly straight line, and I can't draw a perfectly straight line with a mouse, but you get the idea. And what it shows is that if you only study for 1 hour for a test, you're going to fail. Okay. Whoops. And if you study for 2 hours for that same test, you get a D. Study for 3 hours, you get a C. Study for 4 hours, you get a B, and study for 5 hours, you get an A. And you can predict these. Now, and look at the data. I'm not going to do this for all of them, but 4 hours gets you a B. Okay. Now, could you from this relationship predict what would happen if you studied for 3.5 hours? All right. Well, in that particular case, you probably could. All right. 3.5 hours is about here, and so if you look at this, what it indicates is that you're probably going to get a C plus. All right, ish. All right, I know my lines aren't perfectly straight here, but you can use this graph in order to predict what the an outcome is going to be that's not actually in your data sample. Okay. All right. Now, this graph shows another relationship, and there's definitely a relationship. All right. First things first. Before I go any further, I want to make sure that I point out this. I hate this. All right. No graph should ever have a break in it. All right. This number, it starts at 0 and it should go 0, 1, 2, 3, 4, 5, then 6, 7, 8, 9, 10, blah, blah, blah. All right. Now, back to the relationship itself. This one shows the number of errors on a test. All right. And so it shows that if you only study for 1 hour, you make 11 to 13 errors. If you study for 2 hours, you make somewhere between 9 and 11 hours. If you study for 3 hours, you make some 9 or 10 errors. 4 hours, you make 8 or 9 errors. And 5 hours, you make around 7 errors. All right. And so you can see that there's definitely a relationship here. All right. As X increases, Y decreases. Okay. In other words, the more hours you study, the fewer errors you make. And although it's not a perfect assessment, I can't necessarily predict exactly how many errors you're going to make based on the number of hours you studied. I can make a pretty good guess. All right. So there's definitely a relationship here, whether it is one that is 100% predictable is a whole different story. All right. And so, it's not perfect, but there's definitely a relationship here. Now, this relationship, or this graph, again, same set of variables. We've got errors on the test on the y-axis, the number of hours studied on the x-axis. And again, let me point out the break here, which I do not like. But here you can definitely see there's a downward trend here, all right? But the data is far more spread out in this graph than it is in the previous graph, all right? Let's go back. See, the data is much more tightly packed. And of course, it's very tightly packed in this one, okay? We're getting weaker and weaker and weaker as we go through these graphs. And so there's still a relationship. You can definitely say, well, yeah, the more you study, the fewer errors you make, generally speaking. But it's not a strong relationship. Okay, it's definitely a weak relationship here. And so, again, this is why we would need to do a statistical analysis in order to determine whether this whether there was a statistically significant relationship here. Right? Now, in our next graph here, there's no relationship at all. All right. This is the relationship between the number of eye blinks per minute, the number of times you blink, and the number of chocolate bars consumed. And again, let me point out, I don't like the break here. But you can see that the data here is just all over the place. All right. There's no consistent pattern, and therefore there's no relationship between the number of chocolate bars that you consume and the number of eye blinks per minute here. All right, so there's absolutely no relationship in this data. It's just somebody took a pot of spaghetti and threw it up against the wall, and it just stuck in that particular pattern. It didn't have any relationship. Okay, now my personal belief is that the more chocolate you consume, the more you'll blink, because chocolate is mostly sugar, and sugar raises your metabolism, and metabolism kind of makes everything go a little bit faster. But according to this particular graph, there's no relationship between the number of chocolate bars that you consume and the number of eye blinks per minute. Okay? All right. Now, the next thing that I want to clarify is that there are really two kinds of statistical analyses. All right. The first is what we call a descriptive statistic. And that simply describes a data set. It tells you what the average is, what the mean, median, and mode are. These are terms that hopefully you remember from high school classes somewhere. And so they just tell you the general overall characteristics of the data set, whatever that data set happens to be. On the other hand, inferential statistics compare generally two or more groups, and they can tell you whether or not the two groups are different from one another. All right, and so inferential statistics are a lot more complex, and they do tell you a lot more in the end. Now, by definition, descriptive statistics are procedures for simply organizing and summarizing data. All right. Essentially, what they tell you is what scores occurred, what the average or the typical score in a data set is. They tell you if the scores are very similar to each other or if they're very different. In other words, spread out. All right. If you've got a data set and all of the numbers in that data, all the measurements that you made are very, very similar, all right, then the data are very obviously close together. And if they're very different, they're spread out a lot more. All right. So, for example, very similar scores might be, on a test, you get an 89, a 90, and a 91. Okay. The person sitting next to you might have gotten an 80, a 90, and 100. Okay. Now, both of these data sets give you an average of 90. All right. If you don't believe me, do the math, right? 89 plus 90 plus 91 is 270. Divide that by 3 and you get 90. 80 plus 90 plus 100 is also 270. Divide that by 3 and you get 90. So the average in both of these scores is 90. But are the data sets the same? Well, no, because this data set here, all the data points are very close together, but here they're much, much different. Okay, and then finally, descriptive statistics may be able to indicate whether a relationship is present in that set of data. Now, inferential statistics, on the other hand, are procedures. They're statistical tests used for deciding whether the sample data accurately reflect or represent a particular relationship in the population. Okay, and so generally speaking, they tend to be far more complex. They tend to involve mathematical calculations beyond averages and ranges. And they tell you essentially whether two groups of data are different or not. Okay, and so in terms of behavioral statistics, if you're doing an experiment, you'll use an inferential statistic, and you'll compare the experimental group with the control group to see if they're different. All right, and that's what the inferential statistics allow you to draw an inference, all right, a conclusion based on the calculations that you do. All right. If you, is there a relationship between the amount of food that you feed squirrels and how fat they get? All right. Obviously, there probably is, but you have a group of squirrels that get fed 2 acorns a day, and another group of squirrels that get fed 10 acorns a day, and then you compare their weight at the end. Is the weight of the squirrel um, in the control group, the average weight of the control group, going to be different from the average weight of the experimental group? The answer there is, yeah, probably. All right. The experimental group with 10 acorns are probably going to be a lot fatter. They're going to weigh a lot more than the squirrels that only got 2 acorns per day. All right. An inferential statistic will be able to compare those two groups and give you a numerical answer that demonstrates the difference between those two groups. Okay. Now, we've used this word statistic a great deal over the course of this chapter and the previous one. But by definition, what exactly is a statistic? Well, it is a number that results from a descriptive procedure describing a sample of scores. All right. So, 10 squirrels in the control group versus 10 squirrels in the experimental group. All right. You calculate a statistic to describe the differences between their scores, if any. All right, there may not be any differences. Now, why is this important? Well, because a statistic is different from what we call a parameter. A parameter is a number describing a characteristic of a population of scores. All right, now, if there are, for example, 200 squirrels living on the campus of Siena College, and you only measure 20, then what the calculations that you do are statistics. If you measure all 200 squirrels, then you're talking about a parameter, all right? Because you've described or measured the entire population. As we said previously, it's not always possible to get parametric data because it's impossible to measure every single individual in a given population in many cases. So far more frequently, we rely on statistics, which just essentially deal with a sample of the possible or potential data points. Okay, so we're going to leave it there for this video. This is, again, the second of 3 videos dealing with Chapter 2, and I hope you learned something.